just kind of pivot around and look at all the different possible solutions. That was actually a much faster technique, but that technique only works with discrete systems. So if you do want to fully explore a design space where you have continuous variables, that might not be the best option, whereas simulated annealing might be a good option for more continuous variables, especially since jumping around discrete variables it's a lot harder to understand and put a derivative when you're using discrete variables if the values can jump around a lot. So this particular point corresponds to, unfortunately, a rather boring design solution of 2 relay orbits, 1 relay each, but that does give us a mass of the small satellites of close to regular CubeSat mass, relay mass on the order of 30 kilograms, total mass of the whole system. Again, it's not an important number, but it is a good way to look at the system and say, here is our global minimum. Now let's take a closer look at that solution. Now we simplified the orbital mechanics of it by using that variable S1. This is what the orbit propagation looks like for that particular design solution. And we look at the blue line is the worst case scenario. The black line is the worst case scenario. And what we see is that during this 5-year period, we're only communicating with that worst satellite once, out here in the beginning. And then we don't actually communicate with it again until much later. So if we have data that we want within 5 years, that's not a very good way to look at it. If we double the number of relays per orbit, now we have 4 satellites. This is what the latency looks like. Now we're communicating with all the satellites basically twice as often as a result of that. If we take a look at some other interesting design points, such as the 3 relays, 1 relay per orbit case, we encounter a few areas where we're communicating with them more often. And then if we look at the case where there are 5 relay orbits, what we see is that the maximum distance is never really that high. It's 0.7 AU. That's still really, really far. That is, almost 100 million kilometers. We're used to communicating with small satellites on the scale of 400 kilometers. We're talking about massive, massive orders of magnitude in signal attenuation. So in the emergency case, maybe these satellites could communicate with a lot of power. But as we see, the more relays we have, the more opportunities we have to communicate with those satellites. So for the second part of this simplified version, we went into multi-objective optimization, where we took a look at not just the system mass, but also the data throughput. We're minimizing the negative of the system data throughput. We have the same constraints, we have the same primary design variables, same selected parameters for our science requirements, but now we're taking a look at the internal design variables and how those change. We're not just minimizing those. Now we can increase the size of our antennas and take a look at how that affects our communications ability. So one of the method we used to do this multi-objective optimization was NBI, non-normal boundary intersection. Yes, normal boundary intersection. Thank you. And so what that does, if you have it works well when you have continuous variables. It does not work well when you have discrete variables. So for each discrete case, we were able to run this program on it, and that gave us the Pareto front of possible designs within those continuous variables. What we see is that we have a convex Pareto front. We have to add quite a bit more mass at the beginning before we start to see good returns on our maximum data rate. That's because the square law is associated with the size of the antennas and those communication parameters. But once we get to a certain point, then it goes a lot better. We're starting to see more return on investment every time we increase the size of our antenna. Now, we eventually have to stop. I think the limit for the relay antenna diameter was something like 10 meters, which is kind of huge for a satellite out in space. So we do have to put realistic limits on what we can consider the maximum size of everything. So when we look at all the different possibilities, we can see kind of a combined Pareto front. What you expect to see is the more satellites you have, the more data you can get, and that's what we see here. As we go out to these worst cases, these heavier examples, we go 1, 2, 3, 4, 5, 6. When we have 6 relay orbits, that gives us our maximum data rate, net data returns. So if we want to have low mass, we don't have very good latency, but we still get the job done according to the metrics that we came up with before. But if we want to do a better job with communication, we need more satellites, which is an obvious conclusion, but that's what this model is showing as well. And we didn't just use the S1 simplification. We also ran a Monte Carlo analysis, brute force calculation, calculating everything out over the 5-year period, and looking not at the data rate at this worst case minimum distance, but the total data you could possibly transfer throughout the system lifecycle. And so what we see, a comparison, 3 hours and 61,000 designs for this when we simplify versus 20 hours and only getting half those points randomly assigned, we still get to see some of the trends that we want to see, like how having more satellites, 6 relay orbits here at this particular point gives us kind of the best objective, whereas here we see little ordered, this is mostly Monte Carlo chaos you're seeing there. So what we got from this study is obviously the final architecture and how we select that depends a lot on our stakeholder needs and inputs. We need to understand, one of the reasons why I'm here today is I want to talk to you guys about what would a company who is interested in launching an interplanetary communication system, what would they need? What are the things that they are interested in? What are the objectives they want to optimize? Future work will have much higher fidelity models. We're working on adding a lasercom optical communication subsystem model. That way we can do that trade-off and see how much better data rates we can get at what mass cost, and then we can include complexity costs. It's adding up every time. Some of the things we saw from an MDSO perspective was that a model like this where we have both discrete and continuous elements is quite a challenge. Especially with a lot of chaos introduced over long periods of time due to that eccentricity changing. This project didn't really do well with the scaling analysis, but from the trade space exploration perspective, we did learn a lot. And so future work, those science goals that I brought up forward at the beginning, those are actual science goals from a panel of solar physicists, but I need to solicit more of their opinions about what would be valuable from them to really go forward with the study. The idea, or the main goal, is to put this into a responsive systems comparison method, which is the marriage of multi-attribute trade space exploration and epoch era analysis. Then we can really see how a flexible system, federated system, can evolve and change to satisfy more than one set of users. One of the interesting things from the communications perspective is, what if you had a flexible system? This is clearly all within Earth's orbit, but what if we wanted to expand the system so that it could communicate better with Mars? If we had assets on Mars, if we just increased the semi-major axis of those relay satellites, we might be able to communicate with a bigger market of satellites, but at the expense of the satellites that are in the inner solar system in terms of their latency and data rates. There's some big trade-offs we can have there, and it's quite a rich design space, and I would definitely love to hear some of you guys' inputs on what would be important and what's probably not important for now. Finally, we want to take a look at how the scientific instruments we would use and the places we would put them could contribute to synergies and added value as we go in time and have different science goals. With different science goals, we can optimize toward one at the expense of another, or find some happy medium where one set of instruments actually satisfies several science goals, and that's part of the trade-off that we'll be looking at on the science side in the near future. So with that, I will take questions.
Yeah, very good presentation, thanks.
Thank you.
I like the naming a lot, the HOBOCOP. You use the design structure metrics. Is it a parametric approach, or you have to design variables, right?
Yes. Okay. So you mean?
You know the big table.
Yeah, the n-squared diagram.
Identify the concurrent or the loops.
Yeah.
Or parametric design structure metrics.
Yes. Yes. And there are also, the masses of the antennas. Those are not specific.
Yeah.
We used a parametric model that Ignacy and I know about from like 1987. I really want to update that model with more specific information from small satellites. It's just hard to find companies that will let us have that information. Essentially, what I'd like to have is a subsystem mass model. Give me, not just the payload. Give me a mass and a power of a payload, and then I'll build a spacecraft around it. But a communication subsystem. Give me an antenna type, size, and a power, and then I want to be able to calculate the mass of that. Like, I would love to have something like that that's a little more high fidelity and updated than the model I have from 1987. Paul.
So you mentioned a little bit about discretization of variables, and one of them that caught my mind was in considering the total cost by mass. I'm curious what effect the discretization of launches would have on that constraint. I guess it depends on how many spacecraft you can fit on a launch vehicle. If you can fit a large number of them, or maybe a variable amount of them, maybe a continuous approximation is not a bad assumption. I'm curious if you've thought any on those lines about other additional constraints due to the launching orbital placement of the spacecraft.
I haven't gone into too much detail on that thought line yet. I am aware that trying to get a bunch of the satellites placed in certain orbits around the Earth, one way to do that is to launch a bunch at once and then have each one have a small engine module and gradually take it to a further Earth-trailing orbit. Or a slightly more eccentric orbit, and then after one full year they'd be in a completely different orbit. They could burn again to recircularize. With the relay satellites, you could do something similar. It really just depends. There's a lot of launch options, and I don't even know what the best way to tackle that is. But I have thought about it. It's just I don't have any results for that yet.
How do the mass of 3 to 30 kilograms compare to other heliocentric spacecraft?
Incredibly small. So the 3 kilograms is actually, it's a simple magnetometer CubeSat. That's similar to one that was launched. It was the first interplanetary CubeSat where there was, they just put it out there and then they eventually lost contact with it because it was too far away. They were communicating with it for as long as they could. But that was somewhere in the 3 to 5 kilogram range. I don't know exactly, but that's a reasonable assumption. The relay satellites, that seems pretty small. There are definitely some fidelity issues that I need to address, and I would like to talk to some more spacecraft subsystem modelers just to make sure I have those things. You can only look at SMAD for so long before you start to forget what you had before and how it all kind of falls apart. So I'm aware that that is a weakness, and I'm trying to get more eyes to look at that and give me some feedback. Okay, thank you.
Thank you. Okay, so now we have an electronic presentation from North Dakota, from the University of North Dakota. So let's try to connect from Jeremy Stroud.